Kia ora team and welcome to another online tutorial. Today we're going to be talking about the Level 1 NCEA Mechanics exam, question 1, A through D. So I'm just going to quickly expand for question 1 our graph here so we can see it a little bit more in detail. So we have a speed time graph, okay, and it's asking us for to use the information in the graph to compare the speed and acceleration of Danny and Sam in the first 60 seconds, with Danny being our blue line, Sam being our red dash line. We're doing it in the first 60 seconds, and they're asking for speed and acceleration. I'm just going to dot off the first 60 seconds so we know where we're referring to, okay, and identify periods of acceleration and constant velocity for Sam and Danny respectively. Okay, and I'm going to start with Danny and then Sam. As we always do in physics or in mechanics, my first step is going to be writing down the equations. A equals delta V over delta T, okay, for question A. And V equals delta D over delta T. Now for us here, we don't really have to worry about speed or velocity too much because that's going to be provided to us on our y-axis here. I'm going to do Danny first. So acceleration Danny equals our change in velocity, which is going to be 0 to 7, over our change in time, which is going to be 0 to 20. 7 over 20 equaling 0.35 meters per second squared. Okay, remember to give our units wherever we can. Once we get there, okay, he's traveling at a constant velocity, or they're traveling at a constant velocity of that 7 meters a second. Now this acceleration was for 20 seconds. We can then put in his velocity, or their velocity, which was 7 meters a second for 40 seconds to make it to our 60 seconds. Now Sam here, for his delta V, or their delta V, has had a change in velocity of 8 over half the time, which is 10. So let's get our working done. I would say acceleration Sam equals my change in velocity over my change in time, which for us is 8 meters a second over 10 seconds, equaling to 0.8 meters per second squared. Okay. Now again, for our velocity, we don't have to do a calculation because we have a speed time graph, so our velocity is given, and we can see that up until our 60 seconds, he's traveling at 8 meters a second. Okay. I almost forgot my timing in here. So Sam was accelerating at 0.8 meters a second for 10 seconds, and traveled at 8 meters a second for 50 seconds. Now you'll notice that our question here actually says compare. So you would take some time here to actually converse and write your answer on this, saying that Danny accelerated at 0.35 meters per second squared for 20 seconds. Sam accelerated at a faster rate of 0.8 meters a second for 10 seconds. Danny traveled at 7 meters a second for 40 seconds. And Sam traveled at 8 meters a second for 50 seconds. And you could compare that saying Sam accelerated faster and had a higher velocity. Okay, let's move on to B. Now, they've given us some supplementary information here, so let's read along with this. Sam's horse accelerates for the first 10 seconds of the race and covers a distance of 40 meters. Sam and his horse have a total mass of 308 kilograms. Okay, so a little bit of information there we're going to note down in a moment. B, use acceleration to calculate the work that Sam has done with his horse in the first 40 meters. Let's get some relevant information down. Working in physics, remember that we are going to have a look at the relevant equations. So I've got my equations down here down the bottom, and I want work, as the question's asking for, so I'm going to write that down. Work equals force times distance. Now, they provided us a distance, okay, but they haven't provided us a force, so we're going to have to calculate that, and we're going to come down here to have a look at how to do so. So I'm going to use my equation F equals ma, or F net equals ma. Okay, and I'll write that equation down too. F net equals mass times acceleration. From the information provided, we know that the horse, or the combined mass of the horse and rider, is 308 kilograms. Okay. And from our previous question, we know acceleration in the first 10 seconds is 0.8 meters a second squared. So we're first going to calculate the force and then use our force and the distance provided to calculate our work. Let's get to it. So F net equals our mass, 308, times our acceleration, 0.8, and that's going to give us 246.4 newtons. Okay, so we have our force. Now we have both a distance and a force, and so we can calculate our work. Okay, so we're going to say work equals our force, 246.4 newtons, times our distance, which is provided in the question, 40 meters. Okay, and we get 9,856 joules, remembering that it's energy. Now I'm just going to quickly partition off these different sections so I can actually do some working here. And I'm going to answer C over in this section. So it says, explain the work and power if a new heavier jockey was on Sam's horse, which had the same speed and acceleration over the race. It says that calculations are not required, but we're going to look at the equations anyway because they'll help us structure our argument. We know from earlier that work equals force times distance. We're going to look at our equations provided down the bottom, find our one for power, and write that down. Power equals work divided by time. Okay. Because power involves work, we're going to look at the work done first. All right. And to look at the work done, we're going to have to consider the force. So remember that force equals mass times acceleration. Now in the question, it says that the velocity and acceleration remain the same over the race, theoretically. Okay. So what's changing with the force? If our new jockey has a higher mass and acceleration is staying the same, then we're going to get a greater force. Okay, so F net equals greater. Okay, now our work is force times distance, and we're assuming that the distance covered in the race is exactly the same, but the force is increased. So if our force is increased and distance remain the same, then our work must have also increased too. Okay, so work is increased. All right, let's look at the power. Now for our power, our work is increased, but because they're going at the same velocity and have the same acceleration, the time taken is going to be the same. So if our work is increased, but the time stays the same, then there's also been more power. So power has also increased. Now, again, a reminder that you're not going to structure your answer like this. You would put it into complete sentences and write a paragraph. This is purely for workspace. If you want to find a model answer, they are online, but I'm just talking you how to get to that idea. So our jockey, all right, on his horse is heavier, meaning that if the acceleration is the same, force is greater. Because they're covering the same distance with a greater force, more work has been done. More energy has been used or transformed, in this action. And because more work has been done and more energy is being transformed over the same amount of time, okay, remembering that work goes up and the time stayed the same in the race, then the horse has exerted more power with the heavier jockey. Okay, that's C done. Let's move on to D. Well, D states that after 90 seconds, Sam horse has travelled 710 metres. How much further have they travelled compared to Danny and her horse at this stage of the race? So we're going to have to calculate the distance covered by Danny in the first 90 seconds. So we're going to have to mark that off. Okay, figure out the shapes, calculate the area under the graph to get the distance, and then make our comparison. So first of all, what I'm going to do is I'm going to mark off the graph so I know, and this may be small for you, and I apologise for that, what different shapes I'm going to be calculating and where up to I'm going to be calculating. So remember that I'm looking for triangles and squares or rectangles. Okay. So I'm going to take that there. And I've got 1, 2, 3, 4 different shapes to calculate the area of. Now again, remember that in physics, in mechanics, we always try to write down our equations to make sure we don't make any silly mistakes. Okay, and I see a lot of that in students' papers. So I'm going to just write down area of a square equals base times height. Okay, and area of a triangle equals half base times height. Okay, just so I don't make any silly calculations. The distance of Danny, okay, is going to equal the sum of all these shapes, or the areas of these shapes. So distance, Danny, okay, we're going to look at our first shape, okay, which is a triangle. So we're going to use our equation half base times height. Our 2 and 3 are squares. We're going to use our base times height. And again, for 4, we'll use our area of a triangle again. Our first shape 1 is going to be half, or 0.5, times our base 20 times our height, which is 7, okay, plus our second shape, which goes from 20 to 60 for our base. So it's going to be a base of 40 and has a height of 7, okay, plus our third shape, another rectangle, which goes from 60 to 90, so has a base of 30 times 7, okay, plus our last triangle, which is going to be half, or 0.5, times our base of 30, and it goes from 7 to 12, so it has a height of 5. Now, if we do all these calculations and add them up, okay, type them into your calculator, you should get an overall area and covered distance, right, of 635 meters. All right, so that's the first part of our equation. We've done the calculation. Now we're going to look back to the question to make sure we've actually answered it. And it says, how much further have they traveled comparing Danny to Sam? And they've said that Sam's traveled 710, so I'm going to write that down. Distance Sam equals 710. All right, let's figure out the distance there, or the difference between them, sorry. So 710 minus 635, we get 75 meters. Okay, and we can make our statement, i.e. or therefore, okay, Sam has traveled 75 meters more than Danny. Cool. Now that is the first part of the 2017 exam question. Okay. We looked at calculating acceleration and velocity off a speed-time graph, or the mass provided to calculate our weight force, and then using that to calculate work. Okay. We explained how changing the jockey and made to a heavier jockey would affect both the work and power of the horse. Okay. And we looked at the comparative distance traveled using area under the graph to make a comparison between Sam and Danny. Hopefully that's been helpful, team. Hopefully it helps you to get out there and get into some physics or some mechanics. Have a good one.